Hi, my name is Abbie Bradshaw, and today I will present to you some research interested in the role of hearing in speech motor control. We know that the brain monitors the sound of our voice as we're speaking and uses this speech auditory feedback to guide our production of speech sounds. This is important in development as we learn speech sensorimotor mappings. We also know that in the mature system, delaying speech auditory feedback can have a highly disruptive effect on speech production. Further, individuals born deaf with impaired access to auditory feedback from their own voice often show atypical speech articulation. Experimentally, we can probe the use of auditory feedback during speech production by making real-time changes to the acoustics of an individual's voice while they are speaking. For example, if we take the F vowel sound in head and shift the first formant down, we end up with something that sounds a little bit closer to the I vowel sound in hid. We then feed this altered signal back to participants through headphones in essentially real time with a very fast latency. This creates a prediction error for the brain, which it then seeks to minimize through driving unconscious compensatory changes to speech productions. In this case, the participant would end up producing something closer to the word had. One way to use this method is to employ a constant perturbation of speech across many trials. What we then typically observe is a compensatory response that builds up across trials and also persists once the formant perturbation is removed. And this is known as speech motor adaptation. Cochlear implants offer the potential not only for hearing speech produced by others, but for hearing the sound of one's own voice while speaking, which could allow for better sensorimotor control of speech and potentially better intelligibility for those who wish to communicate orally. However, speech heard through a CI is severely degraded, and it is unclear if this would be sufficient to support sensorimotor learning. There has been one previous study that looked at speech motor adaptation to a formant perturbation in CI users, which found that compared to typical hearing participants, CI users showed weaker adaptation and no after effects of adaptation. Overall, however, there was a high level of individual variability in responses in the CI users, likely driven by factors such as age of onset of deafness and age of implantation. An alternative way to study the effects of degraded speech feedback on speech motor adaptation would be to simulate CI speech auditory feedback during production in typical hearing participants. This can allow us to probe sensorimotor learning with degraded speech auditory feedback while avoiding the high heterogeneity in samples of CI individuals. This research therefore aimed to test whether typical hearing participants can show speech motor adaptation when speaking with CI-simulated auditory feedback. Additionally, we also aimed to test whether experience of speaking with this CI-simulated feedback would improve subsequent recognition of CI-simulated speech. To test this, we recruited 32 typical hearing participants, and our experiment was made up of two phases. Phase 1, which tested people's recognition of CI-simulated speech during passive perception, and Phase 2, which tested sensorimotor learning with CI-simulated speech feedback. Throughout both phases, CI simulation was implemented using noise vocoding, a technique that implements a degradation of the spectral content of speech similar to that introduced by a CI. For both phases, we used a level of degradation approximating an 8-channel vocoder, and I have some examples to play you.
The gambler lost most of his money at the races.
I'll just play one more.
The dessert was put in the oven at the start of the meal.
So in our experiment, in Phase 1, participants were tested on their recognition of noise-vocoded sentences, like the ones I've just played you, before and after a training phase. In Group 1, during training, participants heard these vocoded sentences, but whilst the accompanying written sentence was also presented on the screen. This has previously been shown to enhance perceptual learning for noise-vocoded stimuli. In Group 2, we tested a novel training task in which participants instead read aloud sentences and heard their own voice noise-vocoded in real time. We predicted that this production task would result in a greater improvement in recognition than that seen during the perception training task. However, we found that both groups showed a significant improvement, with no significant difference between the training groups. In Phase 2, participants underwent a standard speech motor adaptation task divided into blocks of 50 sentences. Participants first produced sentences without any format perturbations for 2 baseline blocks, one with clear speech feedback and one with noise-vocoded speech feedback. From block 3 onwards, a format perturbation was then introduced to the noise-vocoded feedback, in which F1 and F2 were perturbed in opposite directions, with the direction manipulated between groups, as you can see illustrated on these plots. This perturbation was then removed for a final after effect block. And our main measure of interest here was to look at changes in participants' produced formats from the vocoded baseline block to the final block with the format perturbation. And changes in formats in the direction of the dash arrows would be indicative of adaptation in each group. So that is, people moving their formats in an opposite direction to the perturbation experienced. So I will now project the group average format changes onto these plots. And as you can see, changes in formats in the 2 groups are very small, and in fact, were not significantly different from 0. These black lines are then showing you the individual participant format changes, and as you can see, there's a high level of individual variability in responses to the perturbation with noise-vocoded feedback. Overall, therefore, this research has shown that experience of speaking with real-time vocoded speech feedback enhances perceptual learning for noise-vocoded speech during passive perception. And this effect was found to be of equal magnitude to that obtained through the use of prior knowledge using written cues. However, despite this successful perceptual learning, typical hearing participants were then unable to use this real-time noise-vocoded feedback for successful speech motor adaptation. This could be for a number of reasons. So firstly, it's possible that the degradation introduced by the noise vocoding meant that the format perturbation was too difficult for the brain to detect. Alternatively, participants may not have experienced a sense of agency over this new alien voice, which is necessary for self-monitoring processes to be engaged to correct sensory errors. And finally, it's possible that participants would have shown successful adaptation with sufficient exposure to the noise-vocoded feedback. Thank you for listening.